In this video, we'll continue with section 7.6, and now we'll start to get some real problems that go along with the normal bell curve. That other video was very nice as far as getting some instruction, getting into the idea, and you notice that the key to the normal bell curves is to convert everything to z-scores. That in every problem, whatever our mean and standard deviation, those pieces of information will be given so that we can go back to our old z-score formula, get the z-scores from here, and then we could do the work we were doing on the previous page, using these these charts to get the areas. And if the area is what we want, that's great. And if the area is not exactly what we want, that we interpret to get what it is that we need. So let's jump right in. My first problem, I'm going to talk about that the heights of men are normally distributed with a mean of 69 inches and a standard deviation of 2.8 inches. I'm going to ask several questions here, but that's my basic information. And my first question will be, what's the probability that a man is shorter than 65 inches? So a lot of information, and now we actually get to the question itself, and the question is asking about probability. But now there is a huge hint here, everyone, that earlier, well, we started with basic probability and we just jumped in, how many things satisfy out of how many total possible outcomes. And then we started to see some more complicated situations. Well, if it is binomial, what are we declaring success? How many trials, etc.? And now we get one extra bit. And this is a huge, helpful hint, everyone. You see that word normal distribution? We need to make the bell curve. We need to use those charts that we were just starting and get an area that satisfies what it is that we are looking for. So that really gives us a lot of guidance as to where to go. So, well, normally distributed. There's my picture. And now here, again, I mentioned this earlier, once we get that information, we'll notice that the mean and standard deviation are given to us. As we've always said, we're not trying to play games with units. The units would match here if there are units. The standard deviation, there's no way to hide that information. But just as far as the mean, if they talked about an average height, well, we'd understand. We could interpret that as the mean. But for this first one, I wanted to be literal. Do you want to use that as the population mean or the sample mean? It doesn't matter. The formula will be the same either way. Most people start using the population notation. So the mean, that literally goes through the middle. Now for me, I personally just like to keep track of the standard deviation. That's not really on my x-axis, but we're going to need that information. Okay, well, what is it that we care about? We're being asked about probability, so we're going to need some region. But what's the region we care about? Oh, well, we want the probability a man is shorter than 65 inches. Well, the mean is 69 inches. That's in the middle. 65 inches would be shorter than the mean. So it would be somewhere over here on the left. And I don't want the probability a man is exactly that tall. I want the probability man is shorter than that. I'm looking for this tail region. That shaded region is exactly what is being described in this problem. But as we said, I need the z-scores in order to make these charts work. So I'm going to need to find the z-score that goes with this. Z will be 65 minus 69 divided by 2.8. This arithmetic, it may work out cleanly, but not always. If you do this all at once, make sure you use parentheses. That's one thing. Also realize, remember, going back to the z-score formula, you don't pick and choose. You don't get to pick big number minus small. You got to set it up. Data value minus the mean, all divided by the standard deviation. So I get this ugly answer, and that's where, again, we need the second decimal. So that's why going way back, when we first started finding z-scores, we said it's just a good habit to get into back then. Just as a general rule, go to the second decimal. Don't cut off at the second decimal, round. So I'll get negative 1.43. That is the z-score that goes with that data value. Negative, no surprise, it's negative because it's less than the mean. And I want the left-hand tail. This is a lucky break. This chart gives me exactly what I want. But again, I can't use the 65. I needed the z-score. But the negative 1.43 goes with this, and I exactly want the area to the right, the area in the left-hand tail, which is exactly what I want here and exactly what's given on this chart. So the negative 1.43 is this, and that's it. The 0.0764 goes in that tail, and that's exactly what I want. That's the probability that a man is shorter than 65 inches. But let's keep going here, everyone. Again, we've seen plenty of these little situations just from the previous, how these things can change, so let's get some more practice. This one, a negative z, and the area from the chart is exactly what I wanted. It's not always the case. Number 2. Oh, just very quickly, before I go to a whole fresh problem, if I said, what's the probability a man is taller than 65 inches, I still would have marked this off, but now I would have wanted all of this, everything to the right of that. I still would have found this z-score, and this z-score would have led to this area, but now this would not be what I want. I need to do 1 minus this to give me all of this. So just little changes, taller, shorter, that could really influence whether you shade to the left or to the right, and then that could influence the very end. Are there extra steps after you get the area, or are you done? The last thing I want to point out before we go to a second problem here, notice I wrote my z-score, I got this answer. It is a bad habit to write negative 1.43 equals 0.0764. These are connected, but they clearly don't equal each other. It's this z-score goes with this area. So either get used to writing after the z, write area and then the number, or even better, put that area where it goes on your bell curve. That's the best habit you can get into. Here, I wrote it here. That's exactly what I wanted. I was done. Whereas the other example I was mentioning, I'd write this area here, but this would be the shaded region, so I'd realize I have more to do. I'd use this information to get this information. Okay, so let's do another one. Number 2. What's the probability a man is taller than 68 inches? Seems kind of similar. Draw my little picture here. 69 in the middle. 68 is smaller. Again, give yourself room, everybody. Don't make this so small that your words are right on top of each other. You're not trying to be too representative of distance here. You're just trying to keep track of left, right, keep things in order. That's all. So 68 is smaller than 69, but I want the probability man is taller than 68 inches. So I want all of this as my shaded region. Similar to before, get the z-score. Again, I'd have to round. This will be negative 0.36. I certainly don't mind if you skip that 0, but the 0.36. This was 0.357. Don't just cut off. Again, round. That's where some people get frustrated. They have answers so subtly different than the book, and they can't figure it out, and it's because they used the wrong z-score. You use negative 0.35, you'll get a similar area to what we'll get, but you're not going to get exactly the same thing. That's the small mistake. Okay, but now this is exactly what we were describing in the previous problem after we finished it. If I look up this z on this chart, I get the left tail region, but that's not what I want here. So I'll still use this chart. 0.36 would get me to here. So I get the 0.3594, but put it where it belongs. That goes here. The chart shows you what the shaded area, where that goes, but that's not what I actually want. That's not my shaded area, but that's still where it goes. But I could use that to get this. And I could play some games that this plus this gives me 0.5 and add that value to this over here, or a big picture, all of this is 1 minus the unshaded region to give me the shaded. So 1 minus the 0.3594 gives us our final answer. Now, little things, everybody, where do you put your answer? You know, I'm highlighting it here. I put it at the end here. I put it at the end here. Some people, because there's a lot of little work, you know, they just put their answer next to the question itself. I'm fine with that. There's a lot of little things you could do that I'm okay with. But don't put your answer up here. We're using this, but this, again, this isn't so bad so far, but this area can get a little messy. So don't try and squeeze your answer in here. Do your thinking up here. Think about any extra arithmetic you might need to do, but somewhere at the bottom of the problem, back in the question, make sure you mark that somewhere else to make it clear that's your answer. Okay, next problem, I'm just going to do a tiny, tiny twist on number 2. Number 3, what percent of men are taller than 68 inches? It's almost the same exact question as number 2. And I just wanted to point this out, that we've done this a lot with probability, that if you know the probability that one event happens, then you know the percentage of the time it happens in general. So that's all we're going to use here. That here we found the probability that one man is taller than 68 inches. So if the probability one man is taller than 68 inches is 0.6406, that means 64.06% of men are taller than 68 inches. We've done that a lot in the previous sections, but we've kind of did it in reverse. We've often started with the percent and changed it to a probability, but how we could easily change that at the end. So just one tiny thing, be careful everybody. Probability, you're just getting the decimal. If it's a percentage question, you're doing the same work to get that probability, but then just convert that decimal into the correct percentage. Okay, so that was number 3, but really it was just a slight twist on number 2. And even in general, number 2 just tried to get us to just do a little more, to realize some ideas of complement, realize some options once we get our z-scores and how we can deal with them. So now let's do 2 more here, and then we'll do a full separate problem, a whole new situation. Number 4, what is the probability a man is between, let's do 67 and 70 inches tall. Oh, I especially want to bring up the percentage because that's what we did in the empirical rule. So 64% of the time it happens means the probability is 0.64. Again, we're really starting to see a lot of ideas, how they overlap and just kind of show themselves in subtle variations. Okay, but now to this one. Well, 67, 70 inches tall. 69, still the middle. My mean standard deviation haven't been changing. 67 would be shorter. 70 would be taller. I want that the man is between those two, so I would shade between those two values. This goes back to the previous video. And again, we'll get some other possibilities, but in this one, we've got 2 data values, and those values are across opposite sides of the mean, but it doesn't matter. It's still going to get z-scores, but now I'll have 2 z-scores to find. I'll get 2 areas off of my chart, and then I'll appropriately use them to get what I actually want. So I'll get a z-score for 67 And for that one, let's see what we have here. We get negative 0.71. And then I'll get a z-score for 70. And that will give me positive 0.36. Right, I'll do 70 minus 69 divided by 2.8. And it never hurts to write this out. I'm just trying to, to get us to that next point. So 2 z-scores going on. Just a matter of how you want to use the tables, but ultimately we need this region. If I look up the negative 0.71, would put me here. So the 0.2389 would go out here. That was a negative z, and I found the area to the left of that z. And again, we saw this exact same situation just looking at the z-scores. Treat this as a positive z and get all of this area. This minus this will give you this. Or treat it like a negative z to get this area. Then you'll have to think about how to use these areas to get this area. Several possibilities. I'll do it this time. I'll treat it as the positive. So positive 0.36 gives me the 0.6406, but the 0.64 goes here forever to the left. Notice what I was saying before. I'm not writing the areas over here. They don't help me over here. I'm trying to put them over here so I see what I have to try and figure out what I need. This almost seems like it doesn't help. That gives me more than what I want. Oh, but how much more? This much more. So this minus this. And that will give me 0.4017. And just like we saw up here, that's the probability. One man is between 67 and 70 inches tall. What percentage of men are between these heights would be 40.17%. Okay, one more with the heights of men, because now with this last problem, I want you to realize how we can reverse it. Okay, so problem number 5. How tall is a man that is in the 90th percentile? This is basically the reverse of what we've been doing. Now we're being told about his percentage. Remember, we got to go back. We learned this definition of a percentile back in, I believe it was the end of chapter 4, but we didn't do much with it. We learned about z-scores and we saw a little bit of a use. Now we're seeing much more of a use, but we define that idea of a percentile. That if a man is in the 90th percentile, that means he is taller than 90% of the rest of the men. That's exactly a verbatim definition of what it means. So look, if we draw our bell curve. Again, we still have that same starting information. We're still normally distributed. We're still thinking about our bell curve. And we still have the mean of 69 inches and the standard deviation of 2.8. Now, well, first things first. If a man is in the 90th percentile, he's taller than 90% of the men. Well, I know he's over here, because we always said the mean broke things up, 50% below, 50% above. So if I knew he was only in the 40th percentile, he's somewhere over here, taller than 40%, but 40% doesn't get you past the halfway point. So in the 90th percentile, he's somewhere over here. But look at the reverse in this question. I'm not being told to find a probability or a percent. I'm being asked how tall is the man. I'm being asked about the variable, what we're actually been measuring the whole time, which is heights of men. But we're being told about his percentage. Being taller than 90% would mean this whole area, if you want to shade this, that would have an area of 0.90. We're going to do this in reverse. We're going to take one of our charts, and I could do either one, because if I'm 0.90 in this way, that would mean I'm 0.10 in this way. I'm taller than 90%, which means 10% are left over that are taller than I am. So I could use either chart. And I'll show you this in both. But what I'm going to do is the opposite. We've been taking the z-scores and then going into the middle of the chart to get the right area. Now I'm going to do the opposite. I'm going to find the area closest to the area that we want, pull back to find the z-score. So if I do this setup, I'm going to use this chart, and I want to find the closest area to 0.90. This is not the Price is Right, everybody. It's not about without going over, getting up to closest without going over. It's just purely the closest. So what's the area that's closest to 0.90? Well, these are 0.8s, I'm getting bigger. These are 0.9s, I'm too big. These are too big, getting smaller. Too small, getting bigger. There I am, right around here. 0.8997, I'm less than 0.90. 0.9015, I'm bigger than 0.90. So it's one of these two, and I need the closest to 0.90 to get the z. This is 3 10,000ths away. This is 15 10,000ths away. In this case, this one is closer. So pulling backwards, my z would be 1.28. So this would correspond to a z-value of positive 1.28. Notice how it would have worked the same if I did the other chart. Now, I'd be thinking of just the tail, so I'd be thinking of the 0.10, trying to find the closest area to 0.10. And be careful, everyone. It's so easy to go to a value like this one, and hey, that's 0.01, not 0.10. So be careful about that. So we're not here, we're here. There, 0.1003, that's a little bigger than 0.10. 0.0985, that's a little smaller. But one more time, which is closest? This is a little bigger, but this is closer. And no surprise, when you pull back, you get 1.28. Now, technically, you get negative 1.28, and that would be the z on the left-hand side, but we're on the right-hand side, so it still leads us to z is positive 1.28. That's a little weird the first time you do it, so get some practice with that. But now I've got the z-score. I'm still going to use the z-score formula, but I'm going to solve for x. And we saw that on our last test. It was much more basic. We didn't have to do such hard work to get the z-score. It was more handed to us, but we'll still use the same formula, just solve for x. Cross multiply, treat this like it's over 1. Cross multiply 1.28 times the 2.8 gives me 3.584. 1 times this is just x minus 69. Finish solving for x. Add the 69 to both sides. I get 72.584. This is a data value. This is measured in inches. A man would have to be 72.58.6, wherever you want to round here. Even if you wanted to round to, say, 73 inches, be a little bit rougher. But you need to be at least that tall to be in the 90th percentile. Okay, now, like I said, let's change the context. Let's completely change it up. Let's get away from heights of men, and let's just see a different normally distributed situation. And we'll just get some more practice. How do we actually solve? And we'll kind of see all the aspects that we saw in the previous problem. So our new situation, we're looking at the yearly salaries for employees at a certain company. And those salaries are normally distributed with an average of $52,175 and a standard deviation of $3,840. So a bunch of information, and now my first question, number 1, what's the probability an employee earns more than $50,000? Again, we've completely changed context. Before, our heights in inches, relatively small numbers. Now we're looking at yearly salaries. We're looking at very big numbers, but it still doesn't matter. Normally distributed, we're being asked for a probability. I'm going to draw my bell curve. The average is the 52,175 in the middle. I want an employee to earn more than 50,000. Well, 50,000 is less than that average, so it would be over here. But we want people who earn more than this total. Would give me this as my shaded region. I'd find the z-score, 50,000 minus the 52,175 divided by the 3,840. I get negative 0.57. Gonna head around. I'm gonna get the leading decimal here if you want it or not. Going to my chart. Okay. Negative 0.57. Like I keep saying, I really just stick with the negative z-score chart for most problems. The negative 0.57 would get me to here. 0.2843, but that goes in the left-hand tail. That's not what I want. 1 minus that value, and that would be my answer. We'll get 0.7157. And so variations, but that's number 1. If I said, what percentage of employees earn more than 50,000? 71.57%. I won't repeat that problem. Actually, I'll just do it in the next one. So now let's get to our first page, but still sticking with the salaries. So this would be question number 2 with that problem. What percentage of all employees earn between $55,000 and let's go up to $60,000. Being asked for a percentage, but with good practice, we realize, well, I'll find the probability and I'll convert that into the percentage. So first things first, finding the probability, my bell curve. We've got the 52,175 in the middle. Both of these are bigger than the average. So I'd have the 55,000 about here, and the 60,000 will be about here. I want them to earn between those two. So that would be my shaded region. 2 values. I'm going to need 2 z-scores. For 60,000, 52,175. Our standard deviation was 3,840. I get 2.04. And then my z-score for 55,000. Don't worry about this subscript notation. If you don't like it, don't worry at all about it. I'm just trying to keep track since I have multiple z's, just to make sure I'm seeing them, that they go where they belong. But as long as we're computing and using the areas correctly, it'll all work out. So this one gets positive 0.74, if we round that. They're both positive z's. And again, I pretty much just stick with this one. A lot of variation here. I'm not trying to say this is the best way. I'm just trying to give you one way. Other people, you could find other ways. This positive z gets this area. This positive z gives you this area. This minus this, that would work. Just doing a subtle difference. The negative 2.04 gives me this, the 0.0207. But that goes out here. It goes in the tail. Well, since it's positive, it'll go in the far right tail. And now this z will give me this whole big right tail. So the positive 0.074, I'll look up the negative 0.074, 0.2296. But that goes all the way, that covers all of this, and this minus this. 0.2296 minus 0.0207. I get 0.2089. The probability an employee earns between that much is right there. So the percentage of all employees that earn between that much would be 20.89%. So again, there's nothing special about both being positive. We had other problems where, we were across both sides of the mean and we had to add them. Now we're on the same side, so we had to subtract the areas. Again, you can't just try and memorize when to add, when to subtract. You need to get used to using the charts and just get used to, this is the area, this is where it goes. Well, is that exactly what I want? How can I use it to get what I want? Okay, last problem, number 3. And let's do it similar to the last problem with the heights of men. Let's change it to a data value problem. Okay, how much does an employee need to earn to be in the 25th percentile? These questions, when you're trying to find a data value, it's not always giving you a percentile, but in some way it's always telling you something about the area under the curve, the percentage or the probability that your value is bigger or less than, and we're still going to need to work backwards in order to get the z-score. So we're still in the normal distribution case. Again, that was at the very beginning of the problem, so I draw my bell curve one more time. Still have my mean in the middle. But now, to be in the 25th percentile, you only have a salary more than 25% of the other employees. You're over here, right? You're definitely on the lower side. So over here, this would have an area of 0.25. So now that picture is exactly what I'm looking at when I look at my negative z-score table. So I have that area. Let's get the z that goes with it. So let's find the closest area in here to 0.25. These are way too small, so the 0.25s, I'm somewhere down here. Okay, getting bigger, and here we are. A little below, there we go. A little below 0.25. A little above 0.25, which is closer. They're both kind of almost the same. So this isn't the worst mistake to make, but still, what is closest? That's 14 ten-thousandths above 0.25. That's 17 ten-thousandths below. This one's closer. So negative 0.67. Z is negative 0.67. That z-score goes with that data value. We use the area to get the z, unlike up here where we use the z to get the area. But now that we've got the z, using the formula in reverse. Negative 0.67 is x minus the 52,175 divided by the 3840. Don't forget this is negative, right? Negative 0.67 times 3840 still gives you a negative 2,572.8. Add the 52,175. Remember, this was negative. You're getting a value lower than the 52,000. We get 49,602.2. Well, translating that in the problem, this is a salary, so that would be $49,602.20. That is how much you would have to earn more than 25% of the rest of the employees. There are more other things we can do with the normal distribution. There are optional sections if you go past this, situations that are actually discrete, but you could use this thing called a continuity correction and use the normal bell curve anyway to approximate. So it really has a lot of use. But again, these give you some very good examples of what you should be able to do.